Hi there everybody and welcome back. In this tutorial I'm going to take you through the 2020 paper for depth in chemistry, and this is on the OCR A specification for AS level chemistry. Although if you're studying the full A level in chemistry, all of the modules that are assessed in this paper are still very relevant to your second year examinations. So I'd really recommend that you watch this as well and look for those little gaps in your understanding from modules 2, 3 and 4. You'll notice in my list here that I've also mentioned Module 1, and that's because some of the practical skills that you cover in Module 1 are relevant to the content in Modules 2, 3 and 4. Here we are kicking off then with question 1, and this question is all about nickel and its compounds. Here we're shown that nickel reacts with HCl to form NiCl2 and hydrogen gas. And we're asked to explain in terms of the number of electrons transferred whether nickel is oxidized or reduced. Sometimes these questions say in terms of oxidation numbers, but here we're being told to use in terms of number of electrons transferred. So we need to make sure we're reading the question very carefully and not just reading for what we've seen before in past papers. Here I need to be really specific and point out that nickel has lost 2 electrons. And the way I can tell nickel has lost 2 electrons is by studying the formula of this chloride just here. Each Cl is going to be -1, and the NiCl2 has got no overall charge shown, so therefore I assume the nickel has got a +2 oxidation state. Before it reacted, it had an oxidation state of 0 because it was an uncombined element. So that means that in order to go from nickel to nickel with a +2 oxidation state, the nickel has to have transferred 2 electrons. We also know that metals get oxidized when they react with acids, in accordance with Module 2 of the specification in the acids topic. And so here I'm writing in my answer space that nickel has lost 2 electrons, and I'm emphasizing that that means the nickel has been oxidized. Moving on to part B. A student completely reacts 0.192 grams of nickel with 0.150 mole of HCl. So they are reacting completely with each other. Calculate the minimum volume in centimeters cubed of 0.150 mole per decimeter cubed HCl that the student needs for the reaction. Give your answer to 3 significant figures. Now I've highlighted the in centimeters cubed a bit here because it's going to be important a little bit further into the calculation. This is a really typical 3-marker on amount of substance. This is the kind of thing you can anticipate in the depth in chemistry papers and also in your second year A-level papers as a good, unstructured, can you figure it out what you're meant to do with the balanced reaction equation style amount of substance scenario. They follow a familiar pattern. I'm not saying it's always going to be like this, but look out for moles ratio and then quantity. Here we've got moles of nickel, ratio in the equation, and our quantity is volume of HCl. So look out for this kind of pattern. Using the balanced reaction equation and starting off with the nickel, I'm going to find the number of moles of nickel, which is going to be mass divided by molar mass. So that's the 0.192 grams divided by 58.7 grams per mole. And it gives me a mole value of 3.27 times 10 to the power of -3 that you can see just here. The balanced reaction equation has got the nickel and the HCl in a 1:2 ratio. So I'm going to double, because that's the number in front of the HCl. If I go back up to the equation here, can you see? Since I'm moving through the equation from nickel across to the HCl, I copy what the ratio does, so I double my nickel moles to get the moles of HCl required. And that means my moles of HCl required are going to be 6.54 times 10 to the power of -3 mole. Now, in order to find the volume of the HCl, I need to do moles over concentration. But you'll notice here I've got a little sneaky times 1,000. And the reason for that is what I highlighted up here and what's shown in the answer space down here. I'm being asked to state the volume of HCl that would be required to completely react with the nickel in centimeters cubed. Now, my answer of moles over concentration actually comes out in decimeters cubed. So by multiplying by 1,000, I get it into centimeters cubed as requested by the question. So my correct answer here is 43.6 centimeters cubed. The very next part of the question leads directly on from the moles we calculated up here. Calculate the volume of hydrogen in centimeters cubed, once again, that would be produced at room temperature and pressure. All right, so I've got a gas and I've been told that it's RTP, room temperature and pressure. So that means I'm going to be using the molar gas volume, which is 24 decimeters cubed per mole. But I'm going to tweak that number a little bit to save me some time, since I've been asked to give my answer once again in centimeters cubed. So what I'm going to do here is use my moles of the nickel from my earlier part of the question. Since the nickel and the hydrogen gas are in a 1-to-1 ratio with each other, all the nickel moles that react are going to be equal to the number of moles of hydrogen gas formed. So here's my number of moles of hydrogen gas. I then multiply that value by the molar gas volume, but you'll notice I'm using 24,000, not 24, because that means my answer is going to come out in centimetres cubed for my volume of hydrogen gas. That gives me an answer of 78.5 centimetres cubed. Finally, down here for this page, a student repeats the experiment with 0.192 grams of magnesium instead of nickel. Now, there's actually going to be more moles of metal there. So if I use 0.192 grams of magnesium, since magnesium has got a lower molar mass, that's going to have more moles of metal in. So there's more moles of magnesium in 0.192 grams than there are moles of nickel in 0.192 grams. So you might think that's going to affect the outcome of the experiment. But we're told that we're using the same volume of HCl, and it's at the same concentration as an earlier part of the question. Now, what we calculated earlier was the exact amount, the volume, of HCl required to react completely with the moles of nickel. If by tweaking the amount of magnesium to increase its moles, we think there's going to be a change in the amount of hydrogen gas produced, we are wrong. The volume of hydrogen gas produced is going to be exactly the same. And the reason for this is because the magnesium is now in excess. The HCl is a limiting reagent now because the nickel and the HCl had just the right amount in moles of each other to react completely. By increasing the amount of magnesium moles in this scenario, we're not actually going to change the amount of hydrogen gas produced because the magnesium is now in excess of the HCl. Moving on to part C, and we'll notice that there's a little asterisk next to this question indicating that this is a level of response question. A student is provided with samples of 3 nickel compounds. One sample is nickel 2 bromide, another is nickel 2 sulfate, and a third is nickel 2 carbonate. The student doesn't know which sample is which. Describe the tests that the student should carry out to identify the anion, which is the negative ion, I think it's a real gift that they've written that in brackets, in each sample, and write any equations for any reactions. It doesn't mention it explicitly here, but because we know that this links up to the qualitative analysis section of Module 3, I'm going to use ionic equations for these reaction equations because I know that they're okay. You'll also notice in my answer here that I'm actually, if I just zoom out a little bit, I'm actually giving not only the identities of the full formulae, but I'm giving them in an order of first, second, and third when it comes to my process of going through my answer. And the reason for this is because you are meant to know as part of your specification that certain qualitative analysis chemical tests like these should be done on a single sample in a particular order. And so really I should do them in the order that I'm demonstrating on the page. I said I should test for the carbonate ion first, and then the sulfate ion second, and then the halide ions should then be tested for third. Let's concentrate on what we are identifying in each of these different chemical tests then. Starting off with the first one at the top, which is nickel 2 carbonate. And you'll notice that I've given it a subheading. And the reason for the subheading is because this is a level of response question, and I want to make sure that I'm giving as clear and as organized and as well structured an answer as I possibly can, because I know that that's part of the marking criteria. The anion in nickel 2 carbonate is CO3 2-, the carbonate ion. And to test for this, I'm going to add nitric acid. Other acids are available for this, but nitric acid is a good, safe option to go for each and every time. We're going to observe some effervescence or some fizzing or some bubbles, and that's because of CO2 gas that gets released. And here is the reaction equation. I've included the state symbols here, so I've got aqueous, liquid, and gas, not because the question requested it, but because it's a level of response question, and I know that this is all themed around qualitative analysis and observations. So I'm including my state symbols because they actually were eventually, but I can predict they're going to be part of the marking guidelines. The reaction equation is ionic, as I mentioned before, and it is as it appears there. The next anion is going to be the sulfate ion, and that's SO4 2-. I'm going to add barium nitrate here, and again, other barium-containing compounds are available. I'm going to suggest barium nitrate, though, because I know it doesn't interfere with other tests. It introduces the nitrate ion, which doesn't interfere with anything I'm going to do further down the page. Now, what I'm going to get here to test for my sulfate ion, using barium ions, which is Ba2+, I'm going to get a white precipitate of BaSO4 if the sulfate ions are present. And you can see here, once again, I've given the ionic equation and I've included my state symbols, making that white precipitate. The third anion that I'm going to be testing for is using nickel 2 bromide, the bromide ion. And I'm going to use AgNO3, silver nitrate. What I observe this time is a cream precipitate of AgBr, and here once again is my ionic equation including state symbols. A further test that you could do here to help enhance your answer for this level of response question is to make the point that the AgBr precipitate is also insoluble in dilute ammonia, but soluble in concentrated ammonia, and that was included in some of the finer details in the level of response mark scheme. Moving on to question 2. First off, we've got a quick definition, defining enthalpy change of combustion. It's the enthalpy change when 1 mole of a substance is completely combusted in excess oxygen under standard conditions. Check your mark scheme here, but we must make sure that we mention 1 mole, and we must make sure we mention completely combusted. And I would also make sure you point out under standard conditions as well. Moving down the question, and we've got an obvious calorimeter set up just here. We've got a spirit burner, a beaker of water, a thermometer, all set up here. And in the experiment, we're told that 0.525 grams of cyclohexane are burnt, and the temperature of the 200 centimeters cubed of water changes from 21 to 41 degrees C. We need to calculate the enthalpy change of combustion for cyclohexane in kilojoules per mole. This is a really clear, practical scenario associated to the enthalpy topic from Module 3. And we need to use our Q equals MC delta T calculation here. And you'll notice again, much like an earlier calculation in this paper, I do automatically put the over 1,000 in here because whilst I've not labelled it, but I'll add them on now, I do want to make sure that my units come out in kilojoules here, because once again, it's going to save me a job further down the question. As you can see, I'm using kilojoule units down here. So I do Q equals MC delta T to kick off. The M is going to be the mass of the water, so that's 200 centimeters cubed converted into 200 grams, just there. C is from my data sheet, it's the specific heat capacity of water, 4.18, and 20 is my temperature change. That gives me an answer in kilojoules of 16.72. The fuel moles, not the oxygen moles, the fuel moles is found by doing the mass of the fuel that was used divided by the molar mass of the fuel, and that gives me a mole value of 0.00625 mole. Obviously, you could write that in standard form if you wanted to, which would be 6.25 times 10 to the power of -3. And then my enthalpy of combustion value down here is found by doing the negative Q in kilojoules divided by the moles of the fuel, and it gives me a figure here of negative 2,675.2. So why is my answer negative 2,680? And that's because the question instructed us to give the answer to 3 significant figures. My pro tip for you is, if you're ever asked to give a numerical answer in a chemistry exam, have a check back to see if you've been told about a precision requirement. Next up to part C, the student finds that the experimental value for the enthalpy of combustion is less exothermic than the value in a data book. The student evaluates the experimental results. And we've got a little bit of uncertainty work here. And we're told that the uncertainty in the thermometer reading is positive negative 0.5 degrees C, and the uncertainty in the measured volume of water is positive negative 2 centimeters cubed. Determine whether the temperature change or the measured volume of water has the greater percentage uncertainty. Now you'll notice here they've written the word change in bold, and that's because they know the calculation for percentage uncertainty is the uncertainty margin, so like this plus minus figure here, divided by the reading that was taken for that particular quantity. And when we're doing this calculation, you'll notice here for the temperature change one, my numerator, I've doubled it. And that's because when you have a change figure, so for example, my temperature change here was 20 degrees C, and we're told earlier in the question, the way I've got that, just to reiterate this, is because we go from 21 to 41 degrees C, so my delta T was a temperature change, remember? Here, in order to get that temperature change of 20, I had to read the apparatus twice, and each reading introduces an error. And so here I've doubled my numerator. Another common place where this takes place is if we have a titer, because in order to get a titer, you do an initial reading and a final reading to get a titer. And so you often find that when you're doing this kind of calculation for a burette, that you would double your numerator. You could also consider it if you're doing a heating to constant mass practical. For the volume of the water, because we just fill up a measuring cylinder or a beaker right up to the line once, read it and then use it, we don't need to double the numerator here. When I look at these two percentages, I can clearly see that the temperature change percentage uncertainty is bigger, and I need to make sure I put this supporting sentence in here to emphasize that. Next up, for part 2 of this section of the question, suggest 2 reasons, apart from measurement uncertainties, why the experimental value for the enthalpy of combustion is less exothermic than the databook value. So our value, the student's value, is less exothermic. Now, straight away, that suggests heat loss to the surrounding has taken place. Sometimes in exam questions, like what they've done here with the highlighted section, they will say, apart from heat loss, explain 2 reasons why the experimental value for the enthalpy of combustion is less exothermic. And so I want to give you not only the other reason, but a third that you could use, which I've taken from the mark scheme, should you be presented with that kind of limited response approach. Our second reason here is that there could be incomplete combustion, and we can suggest that whenever we're using a spirit burner in this kind of apparatus setup. But an extra one for you to learn is that we could have non-standard conditions. In the experiment, the water in the beaker was heated for 5 minutes. The student thought that the experiment could be improved by heating the water for 10 minutes. Explain whether the accuracy in the student's calculated value for the enthalpy of combustion may or may not be improved by heating for longer. So here we need to emphasize why it might and why it might not. We've got to be really clear. So first bullet point, we're going to say that this could be less accurate due to greater heat loss to the surroundings. So if you keep heating it for even longer, that's even more heat loss to the surroundings. So you're not guaranteeing that things are going to get any more accurate here. Then, for my second bullet point, it could actually be more accurate, as you will have a smaller percentage uncertainty in the temperature change and in the mass of the fuel burn. And the reason for that is because the denominator in the percentage uncertainty calculation increases. If I just go back up to the top of the page where I wrote the calculation here, if I want to improve the percentage uncertainty, which would be to make it lower, what I could do is increase the reading value, increase the denominator in the calculation. The uncertainty is going to stay the same on the numerator, and that's because I'm using the same kit. But if I was to change the reading value here by making the delta T greater, or by making the mass of the fuel greater, then I could reduce the percentage uncertainty. So it's a bit manipulative, but there you go. Moving on to question 3. This question is about some elements in period 4 of the periodic table. The table shows the melting point and electrical conductivity of 2 elements in period 4. This is a phenomenally popular question for bonding, so we must make sure we understand exactly what's going on here. And it does have links to periodicity with regards to the metal. Use your knowledge of structure and bonding to explain the properties in the table. Now, what we've got here is a melting point comparison and an electrical conductivity comparison. We've got 2 different elements. What I'm going to do is, even though this isn't a level of response question, which I was just double checking, I'm going to use subheadings here because I want to make sure that I'm mentioning all the correct science for each substance, and I'm hitting those specific structure and bonding statements. Then if I feel I need to, and I will do, I'm going to put some specific comparison at the bottom if I don't feel I hit the comparison regarding melting point or electrical conductivity in my description of the element structure and bonding. First off then, calcium. We've got a giant metallic lattice structure. Calcium has delocalized electrons, which are mobile, which makes it a good conductor of electricity. Please don't say anything carries the charge here. That's very GCSE and it won't get you anything at A level. Bromine. Bromine is a simple molecular lattice structure with London forces between the molecules. Lots of people forget to mention this. I would emphasize it. In bromine, and if you're going to talk about bromine, either use its name or use the correct formula, don't just write Br. The electrons are in fixed positions in covalent bonds. So here I'm going to contrast the electrical conductivity. So they are not mobile, which makes it a poor conductor of electricity. Then for my final point here, I've not actually gone into melting point much here. When it comes to melting point, I need to either talk about bonds being broken or intermolecular forces being broken where appropriate. And if I have a giant metallic lattice or a giant ionic lattice or a giant covalent lattice, I need to talk about bonds being broken. But if I've got a simple molecular lattice like I have for the bromine, I need to talk about those intermolecular forces being broken instead. Calcium has a higher melting point because the metallic bonds in calcium, it's a giant metallic lattice, are stronger than the London forces because it's a simple molecular lattice in bromine. And that gets me all 5 marks. Moving on to part B. Calcium reacts with bromine to form calcium bromide. Draw a dot and cross diagram to show the bonding in calcium bromide. Show the outer electrons only. This is really straightforward. Just make sure you watch out for some of the trip falls here. Make sure you have got a 2 in front of your bromide ion, and make sure you don't forget to show the dot as an alternative symbol for the pre-existing 7 electrons, the crosses, that are already around the bromine. Also, don't forget your charges. Make sure you don't put a 2 minus outside the Br. It's got to be 2 lots of the single negative. Next up, and here I've got a bit carried away with the red here because I know that when I've done this question with my own students before, people forget about being specific about the comparison of barium to calcium. The reaction of barium with bromine is more vigorous than the reaction of calcium with bromine, and that's because the barium is more reactive than the calcium is. Now, the reason for this lies in the fact that when metals react, they oxidize, so they lose their electrons. The group 2 metals lose 2. And so here we want to look at why barium is more reactive, rooted in the idea that it's going to lose those electrons more easily. So here my 3 bullet point answer is barium has a greater atomic radius than calcium. Barium has less nuclear attraction on its outer electrons than calcium, and barium has a lower ionization energy than calcium. And my rooting of my answer there is all about how barium is going to lose those electrons in its outer shell more readily. But I'm not using that phrasing. I'm using here my exam phrasing because I know that the examiner likes me to talk about radius. My examiner likes me to talk about nuclear attraction, and my examiner likes me to talk about energy. Part C. The period 4 element selenium is in the same group of the periodic table as oxygen. Selenium and oxygen both form compounds with hydrogen with the molecular formula H2Se and H2O respectively. Then we're asked to write an equation here, and this is a black hole. If you read through this, it is quite tricky. It's completely off spec in some regard. Like, we don't do this reaction as part of AS or A-level chemistry. Here, this is a black hole. This is to test your ability to assemble and balance a reaction equation. It is not worth the 1 mark. This will not likely take you 1 minute. If you can't do this in a minute, leave it and come back to it, because there's far better stuff further into the paper that you're going to have to spend longer on that is 100% recognizable from your specification. Here's the correct answer. Take your time if you have the opportunity to come back to it, but don't dwell on it if you're at this point in the paper. Just move on. It doesn't affect the rest of the question. The boiling points of H2O and H2Se are shown below. You can see that the H2O has got a significantly greater boiling point. H2O has hydrogen bonds between molecules, which gives it that significantly higher boiling point. H2Se has only got London forces. Now, you could mention permanent dipole-dipole forces here as well, because we have got 2 different elements in the molecule of H2Se, so you can assume permanent dipole-dipole here, but it would be London forces because the difference of electronegativity between the hydrogen and the selenium is only very slight. But I suppose without any Pauling scale values, you wouldn't know that. We need a third point here that emphasises the strength comparison, that hydrogen bonds are stronger than the London forces in H2SE. Moving on here, and we start to enter into module 3, bromine reacts with concentrated sodium hydroxide at 50 degrees C, as shown in the equation below. Write the systematic name of NaBrO3, so that's from here in the equation. It's sodium bromate 5, and this 5 here, as you can see I've labelled up, is a mandatory part of your answer, because they've told you to use the systematic name. This reaction is an example of a disproportionation. Use oxidation numbers to explain why and include the meaning of the term disproportionation. That's how I've actually opened the question here. I've said the bromine is both oxidized and reduced in the same reaction equation. That's my definition of disproportionation as applied to this equation. And here I'm demonstrating that the bromine is oxidized from 0 to +5. So that's when it goes from the Br here, which is 0, to the +5, which is in the NaBrO3. And the bromine is reduced from 0, starting off here again, to -1, and that's in the NaBr. Moving on to question 4. Nitrosyl chloride, never heard of it, is used in the industrial manufacture of nylon. The dot and cross diagram for the nitrosyl chloride ion is shown below. And what you can see here are actually some annotations that I made about the dot and cross diagram. I noticed that the central atom was nitrogen. I had a lone pair on there, just one. I've got a double bond from the nitrogen to the oxygen on the left, and I've got a single bond from the nitrogen to the chlorine on the right. And what this made me look for is what is it similar to in terms of the specification content for Module 2. And actually, because the nitrogen here is surrounded by 3 electron regions, so that's the double bond, the single bond, and the lone pair, it made me think of trigonal planar. Then when the question asked me to predict the bond angle, that would be between these two just here, and explain why it has the bond angle, I did base my answer on the trigonal planar shape. So they accepted anything from 112 to 120 degrees, with the 120 degrees actually being the trigonal planar shape, bond angle. And my explanation here is the nitrogen is the central atom, and it's surrounded by a double bond, a single bond, and a lone pair, and all the electron pairs repel each other. Nitrosyl chloride, NOCl, dissociates into nitrogen monoxide and chlorine as shown by the equilibrium below. The nitrosyl chloride is added to a container which is sealed, so it's closed conditions, and the container is heated to 400 degrees C, and the equilibrium is allowed to be reached. Write the expression for the equilibrium constant. No problems here, it's just products over reactants, and don't forget your squared. So that's, when I say don't forget your squared, I mean the power of 2 and the square brackets. In the equilibrium mixture at 400 degrees C, the equilibrium concentration of the chlorine is found to be 0.17 mole per decimeter cubed. The student calculates that the equilibrium concentration of nitrogen monoxide, the other product, is 0.34 mole per decimeter cubed, and that's clearly double of the 0.17. Explain how the student obtained this value for the nitrogen monoxide concentration. And it's because the ratio between the two in the equation is 2 to 1. So they're both being formed, and since they're both starting off from 0, and the relationship between the two of them is 2 to 1 by the balanced reaction equation ratio, I'm going to deduce that the nitrogen monoxide concentration at equilibrium is going to be double that of the chlorine. At 400 degrees C, the Kc equals 0.015 mole per decimeter cubed. Calculate the equilibrium concentration of the NOCl at 400 degrees C. So that's at the equilibrium described on the previous page. What I need to do is write out my Kc again just to have a clear starting point, and then rearrange as a subject of the NOCl squared. Now, don't forget that squared. That's going to be really important for the final stage, because again, when I've done this question before with my own students, I've noticed that people can do this stage really, really well and get an answer of 1.3, but then forget that the NOCl here is squared, so we need to do this final stage where we square root this value of 1.3 to get to the final answer of 1.1. Next up, the temperature of the equilibrium mixture is increased above 400 degrees C while keeping the pressure constant. State and explain the effect on the equilibrium concentration of nitrogen monoxide, NO, with these new conditions. Nice and clear point here about equilibrium shift. Increasing the temperature will shift the position of equilibrium in the endothermic direction, which for this equilibrium is to the right-hand side, based on the enthalpy change from the previous page. There it is. Don't forget that. This increases the concentration of the NO in the equilibrium because that is on the right-hand side. Question 5. This question is about the alcohols A to F shown below, and what you'll notice is I've gone all the way through them, identifying the classification of alcohol functional group that I've got on each already. Which of the alcohols A to F are secondary alcohols? Well, as you can see from my labels here, it's C, E, and F, and you definitely shouldn't suggest any extras. For each extra you suggest, take off a mark, because otherwise, technically, you could just give them all, couldn't you? So it is quite a harsh mark scheme. Balancing the reaction equation is straightforward. Just make sure you choose a good method. So that's carbon, hydrogen, oxygen in that order. If you balance the combustion equations in that sequence, that's carbon, hydrogen, oxygen, then you'll get to the answer much quicker. What's the systematic name of the 2-methylbutane-2-ol? That's alcohol B. Well, here I can see I've got my little labeling here of how I got to my systematic name. I've got carbons 1, 2, 3, and 4 in this long continuous chain. And then on carbon number 2, I've got a methyl group, which is a CH3. And I've got an OH group, which is going to give me the name, therefore, of 2-methylbutane-2-ol, since the methyl and the OH group, the alcohol group, are both on carbon number 2 on a 4-carbon bute chain. Next up, little atom economy question. Alcohol A can be prepared by the alkaline hydrolysis of bromoalkane. Of the bromoalkane, and then you've got the formula. The hydrolysis with aqueous sodium hydroxide is shown in the equation below. There it is, and they've labelled up alcohol A. A student gently heats a mixture of the bromoalkane and the sodium hydroxide for 25 minutes. Calculate the atom economy for the preparation of alcohol A. And so here you've got your desired molar mass divided by the total molar mass of all the products times 100, and it gets you 46.1. Show you're working out for this, because it was a 2-marker for the atom economy, and you never know, you might make a mistake with how you put it in the calculator, and you wouldn't want to miss out on 1 mark. Outline the mechanism for the alkaline hydrolysis. The structure of the bromoalkane has been provided. Show curly arrows, relevant lone pairs and dipoles, and the products. So here I've got my full nucleophilic substitution, and that actually is the next part of the question. Name the mechanism. Be really clear with your curly arrow movement here. You should start this curly arrow at the lone pair on the hydroxide ion nucleophile, and you must make sure you start this curly arrow in the middle of the bond between the carbon and the bromine, showing clearly the correct positioning of the partial charges. Also, don't forget to show both products over here, including that Br-. You don't need to show any lone pairs on the Br- because it's not further use of the Br- in this mechanism. There isn't any continuation of how we use it, so I don't need to demonstrate any lone pairs there. The student decides to prepare alcohol A using the same method as in D, but using a chloroalkane instead of the bromo one that we were given. State and explain how the rates of hydrolysis of the chloroalkane and the bromoalkane would differ. Well, the rate is slower with the chloroalkane, and that's because the CCl bond that we're breaking is stronger than the CBr bond. You can say that the CCl bond has got a greater bond enthalpy if you don't want to just say that it's stronger. But you've got to make that comparison, and you've got to talk about the actual bond in your answer. Be nice and clear about the difference here. Moving on with section F of the question, the structures of A to F are repeated below. So these were shown earlier in the question. And the gist of this question is that one of these is a compound called X, and X is oxidized with acidified potassium dichromate solution under reflux to form a compound labeled Y. And then what they've done is they've got the mass spectrum of Y and the infrared spectrum of Y shown below. What they want you to do is figure out what the structure of X is from the selection, what the structure of Y is once X is oxidized using acidified potassium dichromate 6 under reflux, and you've got to use all of the evidence to support your explanation, and then write the reaction equation of X becoming Y. So, I'm going to analyze the spectrum first then. This is the mass spectrum of Y, and the first thing I've labelled up over here is the molecular ion peak, sometimes called the M+ peak, but I don't like that shorthand if I'm honest. I'm going to label this up as the molecular ion peak, and it's at 86. Now, in my analysis, that's going to tell me the molar mass of compound Y. I've also got here that I've got the fragment ion peak here, quite the tall peak, really, isn't it? This is going to be the fragment ion peak that I'm going to refer to support my answer, and the reason I've selected it is because it's the tallest one. If you're not indicated exactly which one or ones you should be using, then I would go for the tallest one because it's the most likely one to be included in the mark scheme, and you're not expected to start digging through these little tiny peaks over here. For the infrared spectrum, I've drawn a big line up here at 1,500 because this entire region is the fingerprint region, and I'm not digging into that anytime soon. Over here are the ones that I'm the most interested in, and I've got no OH peak, which is really important, as I'll explain in the analysis on the next page. I've got the CH, which isn't very useful at all, actually, but I need to identify it so that then I know I'm not actually saying it's an OH peak, for instance. And here's the really important bit, the C double bond O. That's really important. That's present in carboxylic acids, aldehydes, and ketones at this point in the specification, and so I really want to make sure I acknowledge that. And the reason I've done all these annotations is because they're going to look at the spectra. So if there is something that I forget to include on the next page, but I have mentioned it here with my labels, they can credit you for it. So my full answer, here we go. From the infrared spectrum, I've got the peak at 1,700 reciprocal centimeters for the C double bond O, and I've got no peak for any OH. That's no OH alcohol and no OH carboxylic acid. So I know that Y here is definitely not a carboxylic acid, but it does have the C double bond O. So that kind of makes me think Y is either going to be an aldehyde or a ketone. But let's keep digging. X cannot be a primary alcohol, okay? And Y cannot be an aldehyde, so I'm already ruling out the aldehyde that the peak at 1,700 reciprocal centimeters kind of suggested. And the reason for this is because if you oxidize a primary alcohol under reflux, as the scenario of the question painted, you would produce a carboxylic acid. So Y would have to be a carboxylic acid if X was a primary alcohol. Secondary alcohols, however, will oxidize to ketones, and they don't have that OH group. So there's quite a lot to say in that little triplet of bullet points, but it is all really important. And I've got to translate my thoughts to the page just like that in a nice, clear, well-organized, logical line of reasoning, because this is a level of response question. So take your time going through this and do each type of spectrum in order, in whatever order you want, which you prefer, but I would suggest here the infrared spectrum is going first, like I've done, because the mass spectrum, if I'm going to analyze that fragment peak in much detail, is going to require me to have an idea about what the molecule could look like, and that's why I'm doing that second. Here I'm also emphasizing, because I know that the selection of different molecules from A to F at the start of this section of the question does include tertiary alcohols. I'm emphasizing here that X isn't a tertiary alcohol because they don't oxidize. And if X was a tertiary alcohol, then Y would still be exactly the same tertiary alcohol, and the spectrum for infrared would reflect that. Y is therefore a ketone, and X is a secondary alcohol from the selection. So which secondary alcohol is it going to be? Well, the mass spectrum is really useful for that, because the molecular ion peak at 86 means that the molar mass of Y, the product of oxidizing X, is 86.0 grams per mole. And the fragment ion peak is at 43, and that could be either of these two structures. This one is based on my knowledge that it's likely to be a ketone, and this is based on my knowledge of common alkyl fragments, which I've learnt in my study of the A-level, but particularly I could put a group on here for some branching, for instance, and that leads me towards one of the particular structures, E, from the list of molecules. So it could be either of these two just here. So what about my conclusion? Well, I'm concluding that alcohol X is E from the selection, which is this one just here, and Y is therefore this ketone product, which is what happens, as you can see from this reaction equation, which was requested by the question. This is what is formed when alcohol E is oxidized. If we look at the selection, you could argue, since I know it needs to be a secondary alcohol, why is it not C? And the answer of why it isn't C comes directly from that molecular ion peak at 86, because you can't get a ketone product when C is oxidized that has a molar mass of 86. I hope you found this full walkthrough of the 2020 Depth in Chemistry exam paper really helpful. If you did, I would appreciate if you could give this video a like before you go and consider subscribing to stay updated. There's lots of links on screen now to more organic chemistry and other past paper exam questions that I've covered. And until next time, happy revising.